Okay, so what you started learning about over the weekend in chapter 17, both with reading and with lecture video, is irreducibility and reducibility of polynomials. And like I just said a minute ago, be probably worthwhile to look through old exam questions and talk about how to think through these things and actually work through them to some degree. And feel free to stop me if you've got a question as we go. And as I was looking through exam 3 before class here, I was noticing this one right here, number 19, as being one that is definitely a chapter 17 problem. It says use the mod p irreducibility test with p equal to 2 to help you prove that this polynomial, x to the fourth plus 7x plus 3, is irreducible over q, with an added emphasis to be thorough. And does that mean it's a proof? Well, you probably could think of it as a somewhat of a proof, though I wouldn't be looking necessarily for complete sentences here. And by the way, with the homework that I graded yesterday, sometimes with some of you, I still need to take pictures of them and send it to you. Some of the points were taken off because explanations were not as complete as they should have been. So do work on making sure where requested, either in a proof or if I say give explanation, to be as thorough as you can be. So let's write this polynomial down, x to the fourth plus 7x plus 3. X to the fourth plus 7x plus 3. This is certainly a polynomial that is in ZX, right? Its coefficients are integers. ZX is certainly a subring of QX, because every integer is a rational number. If a polynomial's got integer coefficients, they also can be thought of as rational coefficients. By the way, you might ask a question about this. So I just said ZX is a subring of QX. You might wonder, is it an ideal? You could try the ideal test, and actually what you would see if you tried to decide if this is an ideal in here is you would see it's not. It's a subring that's not an ideal, because it would not be what I've called superclosed. It would not, if you multiplied by a polynomial that had, say, rational coefficients that were not integers, you would not be left with a polynomial with integer coefficients in this example. So that would be an example of a subring that's not an ideal. So the goal is to show, evidently by the problem statement, that this is irreducible over Q. Show f of x, this polynomial, is irreducible over the rationals. And I also gave the hint to use something called the mod p irreducibility test. So we should look that up. This is probably the most useful theorem in chapter 17. Let p be a prime, and suppose you've got a polynomial in ZX, so the coefficients are in Z, the integers, and the degree is greater than or equal to 1, so it's not a constant polynomial. So this is a situation where this possibly could apply. Let f bar of x be the polynomial in ZP. So P is some fixed prime. And we're thinking about a new polynomial with coefficients from ZP, so those would be the numbers 0 through P minus 1, obtained from f of x by reducing all the coefficients of f of x modulo P. So take each coefficient in f of x and reduce it mod p. The if-then statement that is the truth of this theorem is that if f bar is irreducible over zp and the degree of f bar equals the degree of f, then f is irreducible over q. So how does that play out here? It's a little bit bigger for me and you. Well, I said use p equal to 2 here. So I'm going to take f of x and I'll go ahead and write mod 2 here, meaning I'm going to take all the coefficients and mod by 2. So while the coefficient of x to the fourth is 1, so 1 mod 2 is still 1. Which will mean the degree of f bar is going to be the same as the degree of f. That's good. We can't use this theorem unless the degree of f bar equals the degree of f. 7 mod 2 is 1, and 3 mod 2 is 1. There are also other coefficients that are all 0, right? 0x cubed, 0x squared, but of course 0 mod 2 is still 0, so those stay gone. So the question now is this irreducible over z2? Since I'm modded by 2. If it is, if it's irreducible over z2, then f of x itself is going to be irreducible over q. Now, I've been talking about this stuff so far, assuming you remember what reducibility and irreducibility means. Before we go further with this problem, maybe we should look back at that definition. The original definition of irreducibility and reducibility is when your coefficients come from an integral domain that's not necessarily a field. You know, your prototypical integral domain to think about here would be d equals z, the integers. We say it's irreducible over d if whenever you express it as a product, f of x equals g of x times h of x, then either g or h is a unit in d. This is supposed to be similar to the definition of prime number. And that's something I emphasized in the lectures. When you've got a prime number, an integer that's prime, and you write it as a product of two things that are also integers, then one of the other of those two things is a unit. The units of the integers are plus or minus 1, right? Units, remember, are the elements in a ring that have multiplicative inverses. In Z, the integers, only plus or minus 1 have multiplicative inverses. So those would be the units. So when you've got a prime number like, say, 7, you could write 7 as 7 times 1 or negative 7 times negative 1. In either case, the 1 or the negative 1 is a unit. Whereas 6 is not a prime. You can write 6 as 2 times 3, and neither 2 nor 3 are units. So this is supposed to be analogous to that. The concept of irreducibility and the concept of being prime are connected kinds of ideas, though we're going to see in chapter 18 that there is a difference between them in some situations, which sounds a little confusing, but we'll get there. Otherwise, if it's not irreducible over D, it must be reducible. That definition, it's hard to get your mind around. However, when the integral domain is a field, it's easier, it makes a bit more sense. A non-constant polynomial is irreducible if it cannot be factored as a product of two polynomials with a lower degree. It cannot be expressed as a product, means it can't be factored that way. So again, our goal here in this problem is to show this is irreducible over Q. We want to be able to show that you can't factor it as the product of two lower degree polynomials with coefficients in Q. That's the purpose of this. Remember, I said our main application is to factoring, and understanding all about factoring, when you can do it, when you can't do it. It's sort of our main application is what we're getting into here in these last 3 or 4 weeks of class. Whoops. Coming back to, oops. Did I lose the screen here? What happened? There it is. Okay, I guess it's just back there. I am recording for you guys, right? You can see the screen?
No, we can't see it.
The entire time?
Just the last little bit.
I don't know what happened. Oh, I somehow I just clicked out a share screen. Okay. Now you can?
Yeah, we got it.
Okay. So it was just those last 10 seconds that you couldn't see?
Correct.
Okay. Okay. Somehow it got goofed up. Okay. So where were we? So we want to show this is irreducible over Q by showing this is irreducible over Z2. That's what the mod P irreducibility test will allow us to do. Right. This is a new goal. Show this is irreducible over Z2. And again, if we can do that, then we can apply that mod P irreducibility test to conclude that this is irreducible over Q. Now, the second most important theorem in chapter 17 is probably 17.1, the reducibility test for degrees 2 and 3. When you're dealing with a field and a polynomial in that field that has degree 2 or degree 3, then it's going to be reducible over the field if and only if it's got a 0 in the field. And since this is an if and only if, even though it's called a reducibility test, it's also an irreducibility test. You could also say it's irreducible over F if and only if it does not have a 0. Make sense? Essentially, with an if and only if you negate both sides, you still get a true if and only if. Say that again. So it's reducible over F if and only if it's got a 0 in F. You could also say it's irreducible over F if and only if it does not have a 0 in F. So this is a pretty nice test to be able to use to see if a degree 2 or 3 polynomial is reducible or not. However, that doesn't seem to apply here because we don't have a degree 2 or 3, we got a degree 4. However, coming back here, it's not really emphasized in the textbook, but I do emphasize it in the lecture, and I'll emphasize it now. This theorem actually is true in one direction, even if the degree is higher than 3. If the degree of F is 4 or higher, you could still say that if F has a 0, then it's reducible over F. So the right to left implication would still be true. So to start, we're hoping this is going to be irreducible. So we're hoping that it doesn't have a 0, because if it did have a 0, then it would be reducible. But we need to check that. We're trying to show it's irreducible over Z2. It's worth checking to see if 0 and 1 are roots of this. So plug in 0, plug in 1. What we're hoping is we hope we don't get 0. 0 to the 4th plus 0 plus 1 is 1. 1 to the 4th plus 1 is 3, is 1 mod 2. So that's good. We did not get 0. So what does that mean? It doesn't mean it's irreducible yet because it's got degree 4. If it had degree 3, for example, the fact that it didn't have a 0 would mean it's irreducible, and we would be done. But at least this gives us still the chance that it's irreducible. And it also implies that x to the 4th plus x plus 1 would have no linear factors. That's worth writing down as part of your reasoning. This means f bar of x equals x to the 4th plus x plus 1 has no linear factors. You can't factor it as a linear polynomial times a cubic. You could also say, and therefore no cubic factors. So what's left to do? We need to see if it's got quadratic factors or not. Are there quadratics that factor this? Don't seem, as you glance through the chapter, there don't seem to be any theorems that might be helpful there. And the reason is there is none. There are no theorems that are helpful there. You've got to do calculations. How do you do calculations to check to see if this has got quadratic factors? You've got to list all the possible quadratic factors and figure out whether any of them are actual factors. That's actually easier than it sounds. Because we're dealing with Z2, there's a very limited number of possible quadratics with coefficients in Z2. We can list them out, in fact. Quadratics with coefficients in Z2. Well, there's x squared. There's x squared plus 1. There's x squared plus x. There's x squared plus x plus 1. Can you think of any others that have coefficients in Z2, zeros or ones, and they're all quadratics? I can't think of any others. There's only 4 polynomials in Z2x that are quadratics. Z2x itself is infinite, right? Because the degree can be arbitrarily high. But if we're talking a fixed degree, in this case, degree 2, there's only 4 possibilities. And that's true for any fixed degree. There would be a finite number of possibilities. So we only need to check these 4. However, at least 2 or 3 of these can be ruled out immediately because they have zeros in Z2. And if these had zeros in Z2, they couldn't possibly be factors of this because this one does not have any zeros in Z2. X squared has a 0 in Z2. 0 is a 0 or a root. So that rules out that one. This one also has 0 as a root. And in fact, it also has 1 as a root. 0 and 1 are zeros. Again, the word zeros means numbers that make them 0, synonymous with root. This one has 1 as a 0, right? 1 is a 0 because 1 squared plus 1 is 2, mod 2 is 0. Only this one has no zeros in Z2. So this is the only one we need to check. Again, because we don't need to check the ones that have zeros, because if these were factors of f bar of x, The fact that they have zeros in Z2 means that f bar of x would have a 0 in Z2, but it doesn't. Make sense? Make sure you let me know if you have a question. So this is the only one we need to check. How? Well, long division. We want to show this is actually not a factor of this. That's the goal, is to show it's not a factor. Our goal is to show this is irreducible over Z2. So we're hoping this is not a factor of it. Talk about what would happen if it did end up being a factor. But based on the way I phrase this problem, it must not be. So we're hoping when we do long division that we get a non-zero remainder. I think I told you guys this story that when I was in grad school, I was taking really high level math classes, including abstract algebra, and we had to pass these things called preliminary written exams, and they were super hard 4-hour long exams. And it was stuff with fields like this stuff that threw me for a loop and gave me trouble. But Eric Gossett told me, well, why don't you just, instead of just, I was assuming that theorems would always help me. But in reality, sometimes calculations help you. And Eric Gossett really emphasized to me how important being able to do these calculations to help you solve problems was. So we want to do a calculation here. We want to do this long division and see if we get a non-zero remainder. It's long division mod 2. What do I have to multiply x squared by to get x to the fourth? I got to multiply it by x squared. Now multiply that times everything there and write it down here. And then subtract. X to the fourth minus x to the fourth is 0. There's no x cubed term here. 0 minus x cubed is negative x cubed, but mod 2, that's the same as positive x cubed. 0 minus x squared is negative x squared, but mod 2, that's the same as positive x squared. And then bring the x and the 1 down. Multiply x squared by x to get x cubed. Multiply x by everything, you get x cubed plus x squared plus x. Subtract, we get 1. Double check that I have not made a mistake. That look good to you guys? I think so. I don't see a mistake. We can't go any further. That's got a degree smaller than this. It didn't have to be constant, actually. It might have been a linear polynomial. We stop when the remainder has degree less than what we're dividing by. Happened to be a constant here, but it could have been linear. We could have gotten x plus 1 here, and we'd still stop. What does this say? This says, thinking in terms of the division algorithm, this says I can write x to the fourth plus x plus 1 as what I was dividing by, x squared plus x plus 1 times the quotient. There's the q of x, x squared plus x, plus the remainder 1. That's the r of x. And again, the r of x could have been linear here, but the important thing is that it's non-zero. The fact that it's non-zero implies now that x squared plus x plus 1 is not a factor of x to the fourth plus x plus 1, because the remainder is unique, and it's a non-zero remainder here. Therefore, x squared plus x plus 1 is not a factor of x to the fourth plus x plus 1 in Z2x. That's important to emphasize. It could be a factor in Z3x. You know, the answer depends on which polynomial ring you're talking about. Make sure you realize that. Is it likely to be a factor in Z3? I don't know, probably not, but it could be. It's not out of the realm of possibility. And therefore, since we ruled out linear factors and we ruled out cubic factors, and we've just now ruled out quadratic factors, and since Z2 is a field, therefore x to the fourth plus x plus 1 is irreducible over Z2. Subtle point here. Why did I not write an x there? Because I'm just trying to emphasize what the coefficients are from. This thing is a polynomial ring. Elements in there are polynomials with coefficients in Z2. Z2 itself, of course, is just a two-element set, 0 and 1. It is a field. We're saying this is irreducible over that field. So you should make sure you put an x there, but no x there. And that helps us finish because now we can say that this is irreducible over Q by that mod P irreducibility test. This is irreducible over Q by the mod P irreducibility test. Which was the goal of the problem. Whereas this test, even though it's described as a reducibility test, could also be described as an irreducibility test. Remember, it's reducible over F, and if and only if it's got a 0 in F, which is equivalent to saying it's irreducible over F if and only if it does not have a 0 in F, in the case where the degree of F is 2 or 3. This test is only an irreducibility test. You cannot use this to prove something is reducible. If F bar is irreducible, then F is irreducible. I mean, the contrapositive would still be true. If F is reducible over Q, then F bar is reducible over ZP. So in that sense, you could say it's a reducibility test, but that you would never use the theorem that way, because checking whether F bar is reducible over ZP in this context, for the most part, would be checking to see if it's got zeros and checking things via long division anyway. The purpose of the test is to show something like this is irreducible over Q. That's the purpose of the test. What if this had not worked? What if we had gotten a remainder of 0 there, so that x squared plus x plus 1 was a factor, and that would mean this is reducible over Z2? We would not be able to apply the mod P irreducibility test, at least when P is 2, which means we need to try another P, like P is 3. And if that didn't work, we'd have to try another P like P is 5. And if that didn't work, we'd have to try another P like P is 7. And in fact, you could go and try infinitely many different things for P. Now, of course, nobody wants to do that, right? You don't want to do it. I don't want to do it. So we always hope when we use this that it's going to work for P equals 2, hopefully. And if nothing else, maybe when P equals 3, or maybe if nothing else, some value of P that our professor tells us to try. That maybe, could be something like 31 or something. Hopefully not. But in theory, it might never work. That does not mean, however, if it never works, it does not mean your polynomial f of x is reducible over Q if this test never works. Say that again. This test is a theorem. It is always true. If f bar is irreducible over ZP, then f is reducible over Q, assuming also the degree doesn't go down. This is always a true statement. It's just not always useful, because you might keep trying different values of P, and f bar is never irreducible over ZP. It always ends up being reducible. That's what I mean when I say you can't always use it. And again, just because it fails for every p, you can't use it for every p, does not allow you to conclude that therefore f must be reducible. In fact, I believe there's even an example in the exercises. It might be a practice problem that emphasizes that point. Yes, this one right here. Show that x to the fourth plus 1 is reducible over zp for every prime p. So you could not apply the mod p irreducibility test to show this is irreducible over q. However, if memory serves me right, it is irreducible over q. You just can't use that test. The test gives you no conclusion, no matter what you choose for p. Can I clarify anything? That's a lot of writing, more writing than you would have to fit on here if I gave you a problem like this. And what the students 3 years ago had. I guess I made it a fair amount of space, but you know, as far as being thorough here, I guess the thoroughness is not so much an explanation as it is in just thorough calculations.
I have a question.
Mm-hmm.
Why does f bar not having any zeros imply that it has no linear or cubic factors?
Yeah, that's essentially the factor theorem back in chapter 16. If you got coefficients in a field, a is a 0 of f of x if and only if x minus a is a factor. So zero would be a 0 if and only if x is a factor. 1 would be a 0 if and only if x minus 1 is a factor, which is the same as x plus 1. And these two polynomials here and here, those are the only two linear polynomials in Z2X, right? There's no other linear polynomials that you can make, and neither one is a factor of f bar, so it's got no linear factors. Also, with the division algorithm, if it did have a linear factor, it would also have a cubic factor. When you divide f bar by a linear polynomial, and if those are factors so that you get a remainder of 0, the quotient will be a cubic, right? Because when you multiply two polynomials, I'm not proving this, but when you multiply two polynomials, the degree of the product is the sum of the degrees. Like if you multiply, that should make sense. If you multiply a third degree times a second degree, you should get a fifth degree. Degree of f times g is the degree of f plus the degree of g. If you've got no linear factors, you're also going to have no cubic. Because if you did have, again, a linear factor, if when you divide f bar by one of these, you get a remainder of 0, the quotient would have to have a degree of 3 anyway, even if the remainder were non-zero, because of this fact here. Does that make sense? Anything else that I can clarify there?
No, that's good.
Okay. Let's look at this one next. Okay, so we're starting here with a quadratic in Z3X. Z3 is a field. Briefly explain why f of x is irreducible over Z3. Hey, the degree is 2. Sounds like theorem 17.1 will be useful here. The degree 2 or 3 reducibility test. Evidently, if this is going to be irreducible, since it's got degree 2, it's going to be enough to check that it's got no zeros in Z3. Then we get into talking also about ideals here and factor rings and do long division to do various things here. Okay, so let's work through this. X squared plus x plus 2, again in Z3x. So yeah, that theorem 17.1 is what we want to use. The degree 2 or 3 reducibility test, which is also an irreducibility test. We got a degree 2 polynomial. We want to show it's irreducible over Z3. That means we need to show it's got no zeros in Z3. So just check. Do calculations. F of 0 is 2, not equal to 0. F of 1 is 1, not equal to 0. Again, mod 3. And F of 2 that's 8 there, then mod by 3, we get 2, not equal to 0. And those are the only things we need to check because those are the only elements of Z3, 0, 1, and 2. And so we've done part A. By that theorem, this means f of x is irreducible over Z3. Okay, so that's not too bad. You got to know that you need to use that theorem. Excuse me. Part B, based on the fact that it's irreducible, why is the principal ideal generated by it a maximal ideal? Why is this a maximal ideal? Maybe that's not the best way to phrase it. I guess I didn't have I didn't have the word why in there actually. I was going to say that's not the best way to phrase it because explaining why would be difficult because you have to prove a theorem in the book because the truth of this or its falsity is based on a theorem in the book. In chapter 17, you want to know this theorem is the point. Let f be a field and p of x be a polynomial with coefficients in f. Then the principal ideal generated by p of x is a maximal ideal in f of x if and only if p of x is irreducible over f. Okay, that's the point. That is to know that theorem. So it was not a why question. It's really a yes/no question. The answer is yes. You wouldn't have to quote the theorem number on the test, but I will quote the theorem number here. It's theorem 17.5. So you just need to know that theorem. For a problem like this, or perhaps true false multiple choice problem as well, just to know that theorem. Irreducibility of a polynomial when the coefficients are in a field is equivalent to the principal ideal generated by that element being a maximal ideal, which, if you recall from chapter 14, is also equivalent to a corresponding factor ring being a field. This is a corollary of the theorem we just looked at there. This is a maximal ideal if and only if P of X is irreducible over F. Therefore, if P of X is irreducible over F, then this factor ring is actually a field. It's pretty important here. Again, it is related to chapter 14. That's the chapter about ideals. When prime ideal and maximal ideal were first defined, we had this theorem here. The factor ring is a field if and only if A is maximal. Essentially, the corollary is based on that theorem as well. Theorem 14.4. Yeah, this follows directly from the theorem right above and theorem 14.4. Pretty important fact here, this corollary. Okay, we will be both using the corollary and illustrating it a lot. And by a lot, I mean including today, perhaps on Wednesday, perhaps on your test, and after the test as well. This comes up a lot. Why, you might ask? Why is it so important? That's hard to explain until we get there. In a nutshell, it's going to, when we create, it's going to allow us to embed certain fields in bigger fields. Field extensions, I did mention this about a week ago, field extensions. And those field extensions will contain roots of polynomials that in the base field didn't necessarily have a root. And this idea of creating field extensions then is what allows the algebra, you might say, to be more complete. Historically, it's related to the fundamental theorem of algebra and the fact that we'd like to be able to factor every polynomial, in theory at least. It's hard to explain until we get there more fully. Part C is a yes or no as well. And that's the corollary. It is a field. And parts D and E, we're kind of expanding on the fact that it is a field to do calculations, ultimately in E to calculate a multiplicative inverse that would be guaranteed to exist because this is a field. So let's look at D first. Either use long division or the fact that these things are true to determine what this element is. Let's do it both ways. Let's use both long division and these facts to verify or to find A and B so that this is true here. Let's do it with long division first. What's the goal here? The goal is to determine A and B in Z3 so that this is true. And how can that be done with long division? Well, I don't know if you remember or not, but there's various examples in the book where you would take this thing here and divide by whatever polynomial is generating A, which is this polynomial here. And whatever remainder you get, that's going to be what goes here. I can explain why it is in terms of the great sucking sound thing getting sucked into ideals here as we go. But let's do the long division first. So take x cubed and divide by x squared plus x plus 2 in Z3. So now we're doing calculations mod 3. Multiply x squared by x to get x cubed. Multiply. Subtract. 0 minus 1 is -1. Mod 3 is +2. Right? Subtracting. There's 0x squared up here. 0x squared minus x squared is -x squared, but mod 3, that's the same as 2. -1 equals 2 mod 3. 0 minus 2 is -2, which is the same as 1 mod 3. So I did a subtraction. Mod 3. Multiply that by 2 to get this. Multiply 2x squared plus 2x plus 2 times 2 is 4. Mod 3 is 1. Subtract. X minus 2x is -x. Mod 3 is 2x. 0 minus 1. Mod 3 is 2. Right? Double check things. Let me know if you think I made a mistake anywhere. I think this is okay. I'm double checking in my mind here. We can stop there because I'm now at an expression whose degree is smaller than what I'm dividing by. That's the remainder. That's the R of x. Here's the Q of x. So what does this mean? It means I can write x cubed, and let me go ahead and put the plus a here so that we're talking about a coset. X cubed plus a. Well, what does x cubed equal? It equals what I was dividing by, x squared plus x plus 2 times the quotient, x plus 2, plus the remainder, 2x plus 2. And that's the same coset representative because it equals x cubed. All this crazy thing equals x cubed and you can check it by multiplication and simplifying, assuming I didn't make a mistake, but it equals x cubed. But then, yeah, this part gets sucked into A. Why? Because A is the ideal generated by x squared plus x plus 2. So any polynomial multiple of x squared plus x plus 2 is in A. That's what the principal ideal means. All multiples of this polynomial. And being in A means it gets sucked into A. And I can write this as 2x plus 2 plus A. Let's try to confirm that using these facts here as well. X cubed plus A, I could think of as, if I'm going to use this fact, I need to get an x squared in there. I could think of that as x times x squared plus A. I could then replace the x squared with 2x plus 1. Expand 2x squared plus x. And then I can replace that x squared with 2x plus 1. Expand. That's 5x plus 2 plus A, but then mod by 3. 5 mod 3 is 2. got the same answer. This matches this. Yay. I was afraid I wasn't going to get the same answer. But it worked out. Okay, so evidently I did not make a mistake anywhere. It should work out if you don't make a mistake, that you get the same thing. Both of these methods are kind of fun in their own way. I think this second method is more fun, seeing how it works out that way. And again, the reason is based on these things. And the reason this is true is based on the fact that x squared plus x plus 2 is in A. And here, to go from here to here, I'm just modding by 3. Finally, find the multiplicative inverse, which will be guaranteed to exist. This is definitely a non-zero element of the factoring. How do you find its multiplicative inverse? We were able to do this kind of calculation here for x cubed. You actually can do it for anything. I mean, I could have picked x to the 4th, x to the 5th, x to the 6th. I could have picked x cubed plus 2x squared plus x plus 5 or plus 1 there or something. And I could still find an A and B where this is true. So the point that I'm trying to make here is that all elements of the factor ring ultimately can be written in this form, where A and B are in Z3. Which also means, if you think about it, that this factor ring has 9 elements. It's a 9-element field, actually. Because there's 3 choices for little a and there's 3 choices for little b. They're in Z3. 3 times 3 is 9 choices for possible elements in the factor ring, which is a field. This is a 9-element field, this thing. This is one of the 9 elements. It's a non-zero. What's its inverse in this factor ring that is also a field? Because all the elements can be written as a linear polynomial plus a, you just need to experiment to see if you can find the values of little a and little b that make this equal to the unity 1 plus a. Set those equal and see if you can solve for little a and little b. Expand this out. Multiply cosets by multiplying their representatives. X times ax is ax squared. X times b is bx. Trying to solve for a and b. As before, use the fact that x squared can be replaced with 2x plus 1. X squared can be replaced with 2x plus 1. Group together the like terms. The x term is 2a plus b, and then times x. And the constant term is going to be a. There we have it. This gives us a system of equations, one of which is trivial. Little a must be 1. And 2a plus b must be 0. Does this have a solution? Certainly a would have to be 1. Is there a solution for b based on a equaling 1? B would be -2, but mod 3, that's going to be 1. And you can double check if you plug in a equals 1 and b equals 1 here, you get 2 plus 1 is 3, mod 3 is 0. So what this means is that the inverse of x plus a, multiplicative inverse, is x plus 1 plus a. Because we found a to be 1 and b to be 1. If you want to double check it, you can double check it by multiplication. Anything that I can clarify there? These are pretty fundamental calculations to do, as I've been emphasizing. And they are kind of fun when you get used to them. Gotta have some fun with this course in some way. This is supposed to be kind of fun. You know, it makes it more fun, certainly, than doing the reading, perhaps. You know, it's tough going on the reading, I think, but important still. Examples really bring things to life, and you can think about the theorems in the context of the examples, and that may help you believe the theorems just as much as proofs do.
We said 2a plus b, but a is 1 and b is 1.
Uh-huh.
So wouldn't that equal 3?
Right, but it's mod 3.
So that would go to 0.
Yep.
But did you say it goes to 1?
I thought I said it goes to 0.
Then wouldn't the x disappear?
Yeah, it disappears in this equation up here. This is I'm trying to find little a and little b to make this product true. I'm setting these equal, which means these two things would be equal, which means since there's no x over here, that 2a plus b must be 0 and a must be 1. That does have a solution. A is 1, b is 1. And then
Okay, yeah.
those are the coefficients of x and the constant term.
Yep, I got it.
This is at least meant to be the fun stuff compared to slogging through all the theorems. Oh, number 16 is not something. This is something you're going to be looking at here between now and Wednesday. Let's give you a little preview of it here. without fully explaining here. Just to get you in the right frame of mind here. We're almost out of time. What's this problem about? I said, consider the integral domain. D is z square root of -5. Well, what is z square root of -5? Well, it is a ring. And what this notation is meant to imply is that it is all numbers of the form a plus b root -5 as a and b are integers, as they vary over the integers. This is, as you look at this, somewhat analogous to the Gaussian integers. Zi, which could also be thought of as z square root of -1. That was called the Gaussian integers. And you can see these are somewhat similar to each other, except we're using square root of -5 instead of square root of -1. How are calculations? This is a ring. How are calculations done? We could just do an example quick. If I multiplied 2 plus 3 times the square root of -5 times 4 minus 3 square root of -5, you'd FOIL it out. First times first is 8. Outside times outside is -6 square root of -5. Inside times inside is plus 12 square root of -5. And last times last is -9 times square root of -5 squared. Square root of -5 squared would be replaced by -5. And -9 times -5 is positive 45. Plus 8 is positive 53. This simplifies to positive 53 plus 6 root -5. So that's an example of a calculation done in this ring here. These are complex numbers. You could think of square root of -5 as square root of 5 times I if you like, but you don't have to. You can just leave it in these calculations symbolically as square root of -5. This is a ring. In fact, it's an integral domain, so it's got no zero divisors. It's got something called a norm. I'm trying to remember if it's a lecture that did I introduce this in a lecture you already watched, or will it be a lecture to watch today? I don't remember. What is this norm good for? This norm is good for deciding, in particular, the relationship between being n of x being prime and x being irreducible in D. The claim is D is not a unique factorization domain. What does that mean? That means the corresponding the analog of the fundamental theorem of arithmetic actually does not hold. 21 can be factored as in 2 ways in this ring into irreducibles. Notice I'm using the word irreducible here instead of prime. Here's your task. Finish the proof by proving that this is irreducible. Okay. So big picture here is that in chapter 18, we're really trying to understand under what conditions unique factorization holds in terms of primes / irreducibles. We're trying to understand when the fundamental theorem of arithmetic can be generalized. And there are a bunch of tools and definitions that have to be gone through to fully understand that. And this is just a little preview of that. We're out of time. If I do ask you anything about chapter 18 on the exam, it'll either be simpler than what you see here, or we'll make sure on Wednesday that we go through this problem more fully so that you fully understand this. Probably we will go through it more fully. I'm not sure if something like this will be on your exam on Friday or not, but we certainly will go through it more fully on Wednesday. All right, that's it. Have a good day.
Thank you, Dr. Kinney.
You're welcome.